Hello, friends. Good morning, good afternoon, good evening, depending on where you are listening to me. I am back again. This is Festus Sadu, Word of Viruses. This evening, I want to introduce another video on my series on viruses. Today, I'll be talking to us on how viruses reproduce themselves, how they replicate inside their host or in an infected cell. How do viruses replicate? How does viral replication lead to infection? To better understand to answer this question and better understand how viruses cause infection, how they lead to clinical diseases, it will be very, very necessary for us to understand how they replicate. And this replication, viral replication cycle can be described actually in two stages. Number one, the growth curve stage and the specific event stage. Growth curve stage and the specific event stage. The growth curve stage, yes, which is represented by the diagram on the right, is characterized by three stages. Number one, the eclipse. This is the time when the nucleic acid is being reproduced, is being replicated inside. The virus particle does not appear at this time. That's why it's represented by the dotted line. This is followed immediately by an hour later by the latent period. This is the first time when the virus appears extracellularly in the host. This is almost equivalent to the incubation period in patient. And this latent period stage is followed by the yield. This is the time, the maximum amount, which we refer to as titer. This is the time the maximum amount of the virus is found in the cell or in the host. And this is the time you have this is probably equivalent to the acute stage of diseases. I just told us eclipse, latent, and the yield. The next stage is the specific event stage. You can identify 7 steps there. The attachment, penetration, uncoating, the synthesis of both the early and late RNA, the assembly, and the release and the budding, which is represented in the diagram on the right. Like I told us before, and by this time you know, before the virus can initiate an infection, it must recognize a receptor in the surface of the whole cell. If it does not recognize the receptor, an attachment may not take place, an infection may not be initiated. But once infection is initiated, the virus gets access into the cytoplasm of the whole cell. That's what we call penetration. It's followed by uncoating. It has to uncoat. What does uncoat mean? The virus, the capsid is destroyed, leading to the release of the genome. Why does the genome have to be released? Because the genome contains all the genetic information of the virus. Without the genome being released, further replication cannot take place. So what we see in the replication, we see 2 arms. Translation, which eventually lead to the production of the viral proteins, and the transcription, which leads eventually to the production of the daughter viruses. This is followed by assembly. Both 2 components, they come together, they assemble together, and because it's a virus are intracellular infectious entity, the virus must find a way of getting out after the assembly. The process of getting out is what we refer to as the budding. Budding has to take place through the surface of the cell, so that we realize at this time that all the cells are dead, and for the viral replication to continue, and for the virus to continue to live, it must infect another uninfected cell. And thus, the process of replication continues. This is the better diagram of what I've just been saying. This is the virus on your far left. This is the virus, a whole virus. This is an envelope virus showing all the receptors, how it gets into the whole cells, and the red line, the red curving line you are seeing inside the cytoplasm is the release, is the genome and the 2 arms of replication. For envelope viruses, during this process, there's what we call glycosylation. The envelope is added, and the assembly, after the envelope is added, it moves toward the end of the whole cell, from where after assembly, it assembles and automatically finds its way out. A new viron, at this point, we refer to a new viron is formed. And what is the function of this viron? This new viron must find another uninfected cell to continue the replication. Viral replication is governed by the principle of complementarity. What do we mean by that? Negative strand will use positive strands as templates to replicate. That's what we mean by complementarity. Complementarity. A negative strand will use a positive strand. A positive strand will use a negative strand to assemble, to give rise to the new viron. So all I've just been saying is this is exactly what we see. This is the practical inoculation, practical isolation, replication of virus in tissue culture. We use tissue culture for replication or whole cells or in the patient. In the first 24 hours, which is almost coinciding with the eclipse I told us, that nothing is seen. Nothing is seen, as if there's no virus, as if nothing is growing. But what actually is going on? The nucleic acid is being replicated. It's being replicated. 72 hours post-infection. What do we see now? All those white spots are what we call the cytopathic effect. Effect of viruses on cells is called cytopathic effect. So we see at 72 hours. But it's more pronounced after 96 hours. This is corresponding to the yield. This is the best time where we have the largest amount, the highest titer of the virus in the whole cell or in the tissue culture. What do we see after 5 days? We can see now all the cells because nearly all the cells are dying. This will be the worst time to recover the virus because the virus has no other cells to infect. It's therefore dying out. So what am I saying? The best time to harvest your virus, to detect your virus, is 96 hours post-infection. Of course, this may differ from virus to virus. A good example we are seeing here, this is the polio virus, showing a roundish cytopathic effect. But let's see what happens with measles virus. Measles virus carries a fusion protein, and the function of that fusion protein is that it fuses the infected cells together. The first cell fuses with the second, the two cells fuse with the next cell until a multinucleated giant cell is formed. In fact, this is for very perfect eye. In fact, even this is diagnostic already. Not all viruses will form multinucleated giant cells, but one of those viruses is measles. It forms what we call multinucleated giant syncytia, which we are seeing here in this slide. I hope you have enjoyed this short video this night, and I know you have an information you are carrying home. You have a better understanding of how viruses replicate and how they eventually lead to disease. You know what I told us in the previous slide, in the previous video. You know, for each cell that is destroyed, it leads to the destruction of tissues. And for each tissue that is destroyed, it leads to the destruction of organs. And when these cells and tissues and organs are destroyed, we see the virus, we see the clinical manifestation of the disease. Please share with your friends, please, and subscribe. I hope to see you next in my next slide. Thank you very much for listening. I covet your attention. Thank you very much. Good night.